Welcome to This Explainer. Today, we're jumping straight into the logic behind BERTScore metrics. If you're building or testing large language models, you already know the old guard. Metrics like BLEU or ROUGE just aren't cutting it anymore. They rely on exact word matches, which, let's be honest, is pretty limiting nowadays. So we're going to take the complex math behind BERTScore, which solves this exact problem, and break it down into a logical, super easy-to-follow assembly line.
Here's our roadmap for the assembly line. First, the LLM evaluation challenge. Second, tokens and BERT embeddings. Third, the cosine similarity matrix. Fourth, optimal one-to-one matching. And finally, precision, recall, and F1.
Okay, Section 1, the LLM evaluation challenge. Let's look at why we actually need BERTScore in the first place.
Basically, we're trying to compare a ground truth reference sentence directly against what the LLM actually spit out. Let's say our reference text is "the cat sat on the mat," but the generated text, what the model predicted, is "the cat was sitting on the mat." Now, to any human, the underlying meaning is entirely identical, right? But older legacy metrics would actually penalize the model here simply because "was sitting" doesn't perfectly match the exact spelling of "sat." We absolutely need a metric that understands context and synonyms, not just rigid character strings.
To solve this puzzle and evaluate sentences based on their true meaning, we're going to push our text through the BERTScore factory assembly line. Think of it like a sequence of highly specialized stations. At step 1, we tokenize. Step 2, we embed. Step 3, we calculate similarity. Step 4, we match. And step 5, we score.
Moving on to Section 2, tokens and BERT embeddings. This is where we prepare the raw text for mathematical analysis.
First things first, we tokenize both the generated text and our ground truth reference text using WordPiece. Now, the logic behind using a subword tokenizer like WordPiece, rather than just splitting by whole words, is totally crucial here. By breaking words down into smaller chunks, like pulling a root word apart from its suffix, the metric can actually understand variations of words. It doesn't treat a slightly modified word like some unrecognizable alien. Instead, it maps these subword units into very specific token IDs that our system recognizes.
Next up on the assembly line, we take those resulting token IDs and feed them directly into the BERT model itself. This is where the magic really happens. BERT takes these IDs and transforms them into high-dimensional embeddings. It's essentially mapping these tokens into this vast mathematical space where words with similar contextual meanings are physically grouped closer together. This contextual mapping is literally the secret sauce that makes everything downstream possible, elevating the process far beyond a simple keyword search.
All right, Section 3, the cosine similarity matrix, or as I like to call it, the matchmaking phase.
With our embeddings fully established, we can calculate the cosine similarity between every single generated token and every single reference token. This forms a massive similarity matrix. Cosine similarity basically evaluates how closely two contextual vectors align. A perfect score of 1.0 means identical contextual meaning. But for instance, if we evaluate the generated word sitting against the reference word the, well, they have entirely different semantic functions, right? So the mathematical output reflects that with a much lower score, like 0.3. It's just a brilliant way to capture semantic nuance mathematically across every possible word combination.
That brings us to Section 4, optimal one-to-one matching. This is all about enforcing accountability in our pairs.
With our matrix built, we use a greedy algorithm to pair off the words, finding the absolute highest cosine similarity values available. But here's the kicker. There is a strict constraint applied here. Absolutely no double dipping allowed. Every generated token matches at most one reference token, and vice versa. Why does this matter? Well, imagine the model just generated the phrase cat, cat, cat. We definitely don't want it endlessly pairing with a single reference instance of cat to artificially inflate its grade. By enforcing the strict one-to-one rule, we hold the model highly accountable for repetitive hallucinations.
So while sticking to that strict one-to-one accountability, the ultimate goal of the greedy algorithm is to select pairs that maximize the overall similarity score across the entire sentence. It kind of gives the AI the benefit of the doubt. It actively hunts for the most generous, yet mathematically rigorous alignment between what the language model meant to say and what it actually ended up generating. Okay, so we've successfully matched the words based on their deep underlying meaning rather than their exact spelling. But we aren't quite done. How do we turn these optimal matching pairs into a final BERTScore? How does the assembly line pump out a single reliable grade we can actually trust for evaluation?
Let's find out in Section 5, Precision, Recall, and F1.
Time to calculate those final metrics.
First up is BERT precision. To get this, we add together all the cosine similarity scores for our formed pairs, and then simply divide that by the total length of the generated text. By dividing by the length of the text the LLM actually produced, precision answers a very specific question. Out of all the words the AI decided to spit out, how many were actually relevant? This aggressively penalizes the model for hallucinating extra, useless words that just don't map back to the ground truth.
Next is BERT recall. This metric uses the exact same summation of similarity scores from our optimal pairs, but crucially, it divides that summation by the length of the original ground truth reference text instead. This fundamentally changes the intuition. Recall is answering a totally different question. Did the model successfully capture all the necessary information from the original prompt? It penalizes the model for leaving out important facts that were present in the reference.
And finally, BERT F1 brings the whole shebang together by calculating the harmonic mean of both precision and recall, which is very similar to traditional statistics. F1 is the ultimate balancer. It makes sure an LLM can't cheat the evaluation system. A model can't game it by generating one single hyper-accurate word to artificially spike its precision, and it can't write a massive rambling paragraph hoping to accidentally hit all the reference points to artificially spike its recall. F1 demands true balance and quality.
And there you have it. From breaking text into subwords to mapping semantic vectors all the way to strictly grading precision and recall. Now that you deeply understand the logic behind the BERTScore assembly line and how it looks past rigid spelling to grade actual meaning, how will it change the way you evaluate your own language models? Will you ever completely trust an exact match metric again in a world of endless AI paraphrasing? This concludes our explainer on BERTScore. Thanks for joining me.